So um, now what we have done over here is we have created our keras.models are sequential. The first thing that we are sending is an embedding layer where we have set our vocab size to be about 10,000. So make sure that this and this is basically the same. Then we have the embedding size, which is going to be 16, and then we have our input length and our max length. So technically what's happening is these vectors, right? There are going to be a lot of vectors which are going to be created, and what we're going to do is we basically can't understand these vectors, but you can imagine them as these random vectors which are being represented in our vector space. Okay, random vectors. So what we want to do is we want to create some sort of an embedding, some sort of like an embedding where we are basically compressing all of this information, all of these vectors into some sort of like smaller vector, which we can then send to our neural network and make our processing much more easier and to make generalizations about our data set more easier. So we're kind of like reducing the dimensionality of our sentences and of our data set so that when we send the embeddings to our machine learning model, it can then um, understand very quickly from the compressed data as to whether a sentence or a movie review is going to be a positive review. So either it's going to be a positive review or it's going to be a negative review. So that is what embedding is doing. This is like the very easiest explanation that I could give. But again, there's a lot of things that goes into embeddings, and I'll be explaining that into the theory videos. So we have done that. Next thing that you'll see is that you could apply max pooling, but the reason as to why I'm using global average pooling is because it's whenever you want to do your processing or you want to train your model very quickly and you can sacrifice a little bit of accuracy, you're going to be using global average pooling 1D. Also, you will find that when I'll be explaining you the LSTM model is not compatible, so it's not compatible with global average pooling, so you need to remove this over there. Okay, so all right, so one small little mistake that I made was that um, you are not adding a max pooling layer, you are adding a flattening layer, because if you remember earlier from the CNN lectures, we were using some sort of convolutions, and then at the end, before we were adding the dense layers, we were flattening it. So you could add a flattening layer which will have which will increase the accuracy, but it will slow down your training time. But if you can leverage a little bit, you will be using global average pooling 1D. Uh, how does a global average pooling 1D works? Well, the way as to how it works is um, you can over here I've just initialized this layer over here. I have this NP array where I have 10 by 2, 1 by 3, 1 by 1. So this is basically um, if I am not wrong, this is a 1 by 3 by 2 sample array. And then what I'm doing is you can see the sample array over here, and then I've applied this entire layer on this data set. So just send my sample array over here, and then the output shape is basically 1 by 2, and the uh, output is 4 and 2. How did I get this? Basically, what I did was um, okay, so I'll just read this out. Next, you will build the model. The architecture is similar to the previous lab, but you will be using global average pooling 1D layer instead of flattening. After the embedding, this adds the task of average overing the sequence dimension before connecting to the dense layers. You see a short demo here, yada yada yada. So this is the calculation which is being done. So it will grab by the it will grab the first element, first element, first element, grab all of them, add them, and divide it by the number of elements that you have. So 10 plus 1 plus 1, that is 3 elements. So 11, 12, 12 divided by 3, so you get 4. And then similarly, you had again 3 elements, 2, 3, 1. You add all of 3 of them, so 6 divided by 3, and you get 2. So that is how your global average pooling 1D is working. So you can use flatten. I can use flatten over here. I'll show you the summary. It will work. I can also train it, but I'll be sticking to global average pooling 1D. So we're going to compile using a binary cross entropy. The optimizer is going to be Adam binary cross entropy because it's a binary classification problem 0, 1. And then the matrix that we have set over here is accuracy. The number of epochs that we're going to train is going to be 10. This has already been training straight. This has already this model has already been trained on, so I won't be retraining it. Over here, padded was my sentences and my labels were training labels. Similarly, test sequences was my validation data sentences, and you can say it like my features and um, my features or my X data set, and my Y was basically test labels. So I've mentioned that over here that hey, this was my X features and this was my Y. Train it on this, and once you have trained this, okay, I have to train this. Okay, so I'll train this and I'll show it to you. So I'll pause the recording, and as soon as this is done, I'll show you the results. Alright, so the training has completed. We got an accuracy of 0.952 and validation accuracy of 0.815. Now the next thing that we're going to do is we're going to visualize our word embeddings. Okay, so after the training, you can visualize the training weights in the embedding layer to see the words that are clustered together on this website. So I will just copy this website, and then it is able to reduce the 16 dimensional vectors you defined earlier, which was this thing over here. So you'll be able to visualize the word embeddings a little bit, and you can understand as to what's happening. um, so to this, we need to get the weights. So the embedding layer weights are going to be model.layer 0. So first we're getting the embedding layer from the model, then we are getting the weights, and then specifying 0 to get the weights, and then we can see the shape of this. So that is 10,000 by 16. Why was it 10,000? Because there was a corpus or vocabulary size of 10,000. So you can imagine that you had an uh, how do I show this to you? All right, I, I can't think of a way as to how I can show this right now. Um, so basically, it's going to be like, um, yeah, I can't show this right now. Anyways, so the vocab size and the embedding dimension. You run this, and then what you're going to do is you're going to need to create two files which are going to be sent to this projector tensorflow.org. The first one is going to be called your the first one is vex.tsv, which will contain the vector weights of each of the word, and the other one is the meta.tsv, which contains the words in the vocabulary for this. So it is useful to reverse word index dictionary, so you can quickly look up a word based on a given index. For example, reverse index of 1 will return you the OOV token because it is always at index 1. Fortunately, the tokenizer class already provides this dictionary through its index word property. Yes, as the name supplies, it is the reverse of the word index which you've used earlier. So by default, this reverse word index is being executed on its own, which is by this index. So first what we were doing was we said word index, right? To reverse this, we can say index word, um, which will that OOV token will always be returned to 1. So we do this, and then we're going to loop through all of our vocab size, get the words, and then we are going to um, get each of the word, get each of the embeddings. um, I can even show this to you. So it's going to basically get all of the words, uh, and save that into your meta file, and all of the weights will be saved in your um, this vex file. So we have these two things. Let's quickly go here and let me show you this representation very quickly. So over here what we need to do is we need to load